Welcome to the fourth lecture on modern construction materials. We have covered until now atomic bonding, how material structures form, and today we will go on to see how atoms move within these structures, and this is interesting because it leads on to give us the understanding of diffusion, the movement of atoms and particles due to stresses, and then when we go on to talk about mechanical behavior we will understand better the mechanisms which cause that kind of a behavior. Now when we have small movements within the lattice, we have the bonds being separated from the stable or minimum energy distance R0. As you remember from the Condon-Morse diagram, we said R0 is where you have the minimum lattice energy within the lattice structure, and that also gives the highest binding energy or the attractive forces between the atoms. Now when there is a small change between this spacing going from this to the dashed positions, we have the distance now as r, and if there is a small change, just like you would have an elastic spring, there is an elastic behavior, and when this force is removed the atoms go back to the original position. So when there are small changes in the interatomic spacing, as the interatomic bonds are stretched, the deformation is elastic. Elastic means that the deformation is non-permanent. When you release the load, the atoms go back to their original positions, but they could be movements or changes that are larger changes in interatomic spacing, and again using the Condon-Morse diagram we can explain what could occur. So here on the top we have the Condon-Morse diagram, and you have the energy versus the interatomic spacing R, and you have indicated here R0, which is the stable interatomic spacing corresponding to the minimum energy in this curve, the minimum potential energy or the minimum lattice energy. Now from this we saw in the earlier lecture how we can derive a stress spacing diagram by differentiating the energy curve, and here you have now this curve which gives us the force F, which is a du derivative du by dr, and this is the distance or how much the atoms are disassociated. Now this curves tell us the behavior between the spacing r and the force, and we find here that over a certain range that corresponds to distance less than r0 we have repulsion or compressive type behavior. Here the atoms are closer to each other than the stable distance r0, and then as there is more tension or the separation of spacing with r being greater than r0, you have this curve which is on top of this dashed line. This point corresponds to the place where you had the minimum energy, and this corresponds to the zero force situation where the atoms are separated at a stable distance. Now as you separate the atoms more, you have a linear part and then a non-linear part and a maximum part. So this, as we said earlier, gives us the tensile strength. Further separation encounters less attraction until the atoms have no attraction anymore and they can be fully separated. This behavior is better seen here where you have this blue curve showing us the case of strong bonding, the force versus distance diagram, and you see here that initially you have a straight line behavior or a linear behavior both in compression and tension. For weak bonding also it is a similar case, but the slope is less. So here you would have more resistance to separation initially, here there would be less resistance to separation, or in other words the modulus of elasticity for the case of strong bonding will be higher, you have a higher Young's modulus, and here for a weak bonding you have a lower Young's modulus, there is less resistance to movement, and beyond a certain stage you have a non-linear behavior, and then finally failure or complete separation of the bonds will occur. Now when we go to large atomic movements, there are some mechanisms which control such movements. Ideally in a crystal the movement of atoms will be very difficult because of the energy barriers, the high energy barriers to motion through the lattice, that is the energy required to have movement of atoms through an ideal crystal is very high. However, defects provide low energy paths, and we find that lot of times defects dominate the atomic movement because they provide these low energy paths. The defects are also responsible for the mobility of atoms under external stimuli, that is temperature, stresses, chemical action and so on. So you find that the defects that we saw in the previous lecture, the point defects, the line defects, the surface defects and so on, affect how the atoms can move within the crystal structure or the lattice structure. There are three basic mechanisms which are important. Atomic movement can occur through slip along atomic planes, dislocation movement, we talked about dislocations already, and diffusion. Now we look at these type of movements in further detail. Starting with the slip along atomic planes, we have what is called plastic deformation, that is permanent deformation or deformation that remains after the load is removed in metals due to the slip along the atomic planes. Remember a couple of slides back we had looked at elastic deformation, where when we remove the load the position of the atoms returns to the original state, that is the atoms return to the original locations and there is no deformation that remains after the load is removed. Now in plastic deformation there is permanent deformation or deformation that remains even after the load is removed, and this, the amount of deformation, the amount of slip that occurs between the atomic planes depends on two things. How much is the external stimuli in terms of stress, or the magnitude and direction of the shear stress. Shear stress is what causes the slip, the magnitude and the direction in which the shear stress is acting, which is based on the external loads and stress causing phenomena. The second aspect is how well the atomic planes are bonded. Better the bond, stronger the bond, less will be the extent of slip under the same stress. This is what we saw a slide earlier. And also what is important is that when we have a lattice structure in a crystal, the slip occurs along planes in which the atoms are most closely packed. That is, if you have a close packed structure along planes, slip will occur along those planes, not across those planes but along those planes. This we see better in this diagram. So you have here a structure with a closely packed atoms. So all these planes here are the packed planes, and if you apply a shear force, then what you will see is that the slip does not cut across the closely packed planes but along those, like what we see here. So here you see how slip occurs, the slip is occurring along the closely packed structure and not against it or across it. This is done, this happens because this requires the least energy for creating the slip. Independent of how the load is applied, slip may often occur in a certain direction. For example, here we see a bar of zinc being pulled and we see that the slip occurs at 45 degrees to the applied tensile force. So even though the force is acting here vertically, we find that the slip is occurring 45 degrees because that is where you have the shear stress acting. Slip requires shear stress and slip occurs in the direction of the shear stresses. So that is why in this case you have slip occurring along the planes at about 45 degrees to the direction of the applied tensile stress. Now when you take a crystal, there will be several atoms packed together in a crystal. Slip in a single crystal now starts in the most favorably oriented slip system, and we have already discussed that slip will occur along the planes where you have a close packing. So slip will occur along the most favorably oriented packed plane, and this when the shear stress along that plane reaches the critical value where the resistance offered is not enough to keep the atoms from slipping. So if you look at this material and you look at just this crystal or grain, they could be closely packed atoms along these planes which start slipping. So they form a slip band. So these are different slip bands which occur due to the shear stress which is given rise to by the applied stresses. These slip lines are very small, almost in the atomic scale, and also separated by a certain distance. This is within a certain crystals. Now we should keep in mind that the crystal planes will not coincide from one crystal to the other. We already looked at this when we discussed polycrystalline materials. So the slip which occurs in one grain, when it has to be continued in another grain, might have to change direction to accommodate direction of the planes in the adjacent crystals. Other than slip, you can also have deformation within the lattice due to twinning, and here you see what happens when you have a structure here which is subjected to shear. So you are trying to make the material shear, then this give rise to a structure like this where you have a twin formed over a certain distance, and here you can see the symmetry about this line, and that is why it is called a twin, and this is called the twinning plane. So this is also a sizable deformation, plastic deformation that can occur in the material, and this mechanism does not require slipping because it occurs due to twinning. When we compare the two, we can see the difference here. Slipping occurs on the plane where the shear stress is applied, with atoms now shifting by one lattice spacing. Twinning on the other hand requires a lot of deformation to occur, like you see in the bottom diagram. So this is twinning. You find that lot of the spacing has to change for twinning to occur. Here you just have one atom shifting each time at each step to have the slip occurring. Now when you see a polycrystalline material such as say copper, you have now different crystals, and you can see the crystal planes along which slip will occur, and if you apply load, you find that slip will occur along this red line in this crystal, but to continue it will have to change direction and slip will have to occur along another direction in the adjacent crystal. So slip planes and directions change from one crystal to another, and materials therefore with more slip systems will undergo plastic deformation more easily. That is, if this adjacent crystal has a slip plane along a similar direction as this, then the continuation of the slip will be easier and there will be more plastic deformation, or plastic deformation will occur more easily under a certain load. This can be explained more by looking at this diagram where we are comparing two structures, the FCC structure, the face centered cubic structure, and the hexagonal closely packed structure, on the right, aluminum and copper have the FCC structure, and you see here shaded different planes along which slip can occur, and you see that these planes are having different orientations. The HCP structure has 3 parallel planes, and all of them, since they are along the same direction, will offer more resistance to an arbitrary slip system forming. So, we find that materials with an FCC structure are more malleable and ductile, which requires a lot of slipping to occur when shearing occurs within the system. So, HCP structured material or metal will be less malleable and ductile, because the formation of the slip planes is more difficult in a polycrystalline material which has the HCP structure. Now, another type of movement is dislocation movement, where we have the defects moving within the system. You see here in the bottom animation that there is a dislocation movement which ends with slip occurring along this line, and an ultimate displacement in the system which is called the Berger vector. There was a dislocation here which moved across and ended up with this sort of a permanent deformation equivalent to the Berger vector. So, atomic movements are easier when dislocations are present. Atomic movements are significantly easier in the vicinity of the dislocations. The slip occurs by movement of the dislocation across. We saw the dislocation moving across here with only a few atoms involved in the slip. At each step there was only one bond being broken and formed, and finally the net result is a shear deformation, permanent deformation called the Berger's vector. We have discussed basically how dislocations move within metals and how deformation occurs within metals, because dislocation movement is easier in metals because the bonding is non-directional. So, dislocations can move without hindrance due to the directionality. There are closely packed planes which facilitate the slip, so that if a dislocation here, it can move across and slip can occur along this plane easily. However, when we look at covalent and ionic solids, it is obvious that it can become very difficult. The motion due to the dislocations can become very difficult, because if you see here, the covalent solids will have angular bonding, directional bonding, and when the dislocation has to move, then the directionality will have to change, and this impedes the movement of the dislocation, because these angular bonds have to have a certain direction, and these cannot be broken so easily, and slip cannot occur in this plane very easily. In ionic solids, if you remember, we had both the cations and anions in a certain array, and now when the dislocation has to move across, it will find that there will be neighbors with the same charge. So, if this has to move, you will find that the cation will have to come here at some stage, and there will be a repulsion between the cations, and this will again impede the dislocation within an ionic solid to move. So, we have basically movement of dislocations in metallic solids because of the type of bonds and because of the type of structure that occurs in metals. We also saw earlier that in polycrystalline materials there are grain boundaries, and at the grain boundaries we had discontinuity of the crystal structure. This is what we call a surface defect, where there is a gap between adjacent atoms, adjacent cations in say a metal, and the slip plane does not continue across to the neighboring grain. Say in grain A, if this was the lattice structure and here you have a dislocation, this crystal plane does not continue into grain B. There is the grain boundary here, and if this dislocation now has to go across, slip to the grain boundary and continue due to a sustained shear, you find that now it has to change direction. This offers more resistance. So, there is a greater force will have to be required to create shear that will continue on to grain B. So, this gives rise to a very important aspect, which is that grain boundaries are barriers to slip. More grain boundaries means there are more barriers, and what happens is this barrier strength, that is which requires a higher force to move the dislocation from one grain to another, increases with the misorientation, that is the angle between the crystal planes across the grain boundary. Here you see between the green line and the blue line there is an angle which is not 180 degrees. If it was 180 degrees, the dislocation would just move across, but now the dislocation has to change direction and move across the blue line for the slip to continue to occur. So, the strength of the barrier increases with more misorientation. More different the angle is from 180 degrees, you have a higher barrier strength, and there is a very high probability that this will occur in a polycrystalline material. Consequently, what we find is smaller grain size within the structure, more barriers to slip, and the strength of the material or the resistance of the material to slip increases. We find that impurities or defects that distort the lattice also offer barriers to dislocation movement, and this we can understand from the figures below. You can have a substitutional impurity where either the impurity or the extraneous atom is smaller than the other atoms or bigger. In both the cases you have a distortion of the crystal planes. So, when the dislocation has to now slip across, it encounters a surface that is not plane, but it is distorted. So, the dislocation now has to surpass this distortion and move across, and therefore, we require a higher shear stress than when there would be no defect and the slip plane is straight. Here also you see that there is a bump. So, the dislocation now has to surpass this bump and go across, which requires a higher shear stress than if this slip plane was plane. So, impurity atoms, atoms that are introduced into the lattice, distort the lattice and therefore generate a local strain, and this becomes a barrier to dislocation movement. So, we saw this earlier in the example of copper with different atoms introduced, say tin, that distorted the lattice and therefore the strength, the yield strength increased, because the yield depends on the slipping and the shearing along the crystal planes. Another type of movement within materials is done by diffusion, is due to diffusion. Lot of reactions, lot of processes that we have in materials which define how the material structure forms and also how the materials behave in time depends on atomic diffusion. So, many reactions and processes rely on the transfer of mass within a solid or a liquid or a gas, another solid phase, and this transfer is accomplished by diffusion, which you see in the animation below, where you have the diffusion of the red and the blue atoms occurring in time. So, this phenomenon of atomic motion is called diffusion, and this is important for several reasons. We can have diffusion joining particles through sintering, where you have in the upper diagram particles that are pushed together, probably heating is applied, and you find that the atoms now move across, and you have a neck being formed in the sintered product. The diffusion now has joined these particles together to form a more solid structure. Diffusion can also occur in metals, and an example is in a diffusion couple where you have bars of different metals closely in touch with some heat applied, and the diffusion now occurs between the two bars. This is called interdiffusion or impurity diffusion, and that you see here in these figures more clearly. We have copper and nickel, two bars say of copper and nickel put next to each other, they are pressed together and heat applied. Before diffusion occurs, we find that 100% of the left hand side is copper, on the right hand side you have 100% nickel. So, the concentration profile looks like this, you have 100% copper and 100% nickel on the right hand side. Now, when diffusion starts, because of the pressure applied and the heating, copper atoms start moving from the left to the right, nickel atoms start moving from the right to the left. So, the concentration profile now changes, there is no sharp difference between the copper part and the nickel part, but you have an area which has both copper and nickel atoms, or an alloy is formed or a solid solution is formed with both copper and nickel, where the concentration is now like this. So, diffusion has created an alloy in the middle and also bonded the two bars together. So, to recap, we have a couple, two bars of different metals pressed together, heated for an extended period of time and cooled. Now, before heating, the concentrations of copper and nickel in the respective bar, in the previous figure we saw on the left it was copper, right it was nickel, and it had 100% copper, concentration of copper on the left and 100% concentration of nickel on the right. But due to diffusion which is occurring due to heating, an alloy is formed in the diffusion zone with a combination of copper and nickel, but the concentration is higher as you move away from the diffusion zone of one material and is a mix at the diffusion zone itself. Diffusion can also occur within the material. In a pure material also you can have diffusion occurring, where atoms move around responding to external stimuli. Say here if we label some atoms A, B, C, D like you see in the left hand side diagram, after some time due to the application of heat or stress you can find that they have changed locations and now they are in the new locations which are shown here. So, this is called self diffusion. So, diffusion can occur within a certain material or due to one material moving into another material. Diffusion is therefore a stepwise migration of atoms from lattice site to lattice site. Within the lattice structure, step by step the atoms are migrating, this is called diffusion. Now, for this diffusion to occur or the migration of atoms to occur within the lattice structure, two conditions have to be satisfied. First, there should be an empty adjacent site because the atom has to shift there. The atom should also have sufficient energy, this can come due to stress being applied, heat being applied. The atom must have sufficient energy to break the bonds, that is keeping it in its place. It has to break the bonds with its neighbor atoms, cause some lattice distortion and move to the new site. So, these are the two conditions which have to be met. We have two possible ways that diffusion can occur. Interstitial diffusion is where the atoms migrate in the space between the parent structure. So, interstitial diffusion involves atoms that migrate from one interstitial position to a neighboring one that is empty. So, you see that in the lattice formed by the blue atoms, you have these small red atoms moving in the interstices, that is the space between the blue atoms. And this occurs a lot in the case where impurities diffuse into a material. For example, diffusion of impurities such as hydrogen, carbon, nitrogen, oxygen, which have atoms that are small enough that they fit into the interstitial space. So, this is interstitial diffusion. Vacancy diffusion is where you have an atom moving to a space which is unoccupied by any other atom. So, you have here, see the blue atoms moving to a space which is empty. This is called vacancy diffusion, and this involves the interchange of an atom from a normal lattice position to an adjacent vacant lattice site, and this obviously necessitates the presence of point defects. If there were no vacancies, then this type of diffusion cannot occur. When we compare the two, the substitutional or the vacancy diffusion and the interstitial, you find that the interstitial will require less energy, less activation energy. Q here is activation energy, Qi is in the case of the interstitial diffusion. You have the small atoms moving from one interstice to the other, and this requires now less energy than a substitutional or a vacancy diffusion, where the bond has to be broken and there has to be significant energy for distortion to be overcome and a new position of this black atom has to take place. So, when an atom diffuses through a crystal lattice, it must move from its equilibrium position where it was before the diffusion occurred through a point where there are strong repulsive forces from its neighbors, and in addition the lattice has to be distorted. This causes an energy barrier. This hump you see is the energy barrier. The energy that is required to overcome this is called the activation energy, and we find that the activation energy for a substitutional or vacancy diffusion is higher, as we see here, whereas in interstitial case the activation energy is less, because this atom is small enough, the distortion is less, and the diffusion occurs more easily. Diffusion is governed by what is called the Fick's law, and this diagrammatically is seen here. You can have a case where you have a change in concentration of what are shown here as black and white atoms, with more black atoms on the left hand side and less black atoms on the right hand side, or more white atoms. So, there is a difference in concentration of the black atoms through this distance x. What diffusion will do is try to make the concentration the same throughout the distance x by having the black atoms move to the right and the white atoms move to the left, to eventually reach a system like this, where you have an equal distribution of black and white atoms throughout the distance x. So, the concentration changes from AB of the black atom to something like this CD, where the concentration is same everywhere over the distance x, or the gradient now drives the diffusion until the gradient becomes 0. AB is the initial concentration gradient, CD is the final gradient after a long time. So, you see the flat dashed line. This is represented by Fick's law, where J is the amount of material moving across a unit area of the plane in unit time. This is proportional to the concentration gradient given by dC by dx. The proportionality constant is d, and there is a negative sign. So, J is equal to minus d dc over dx. D is called the diffusion coefficient, and here x is the direction along which the concentration is acting or diffusion is occurring. The diffusion coefficient is expressed in meter square per second. This diffusion coefficient varies from one material to another. How the solutions are occurring, that is what is diffusing in what, defines the diffusion coefficient, and also importantly we find that temperature also controls the diffusion. You see here on the right hand side diagram several of these blue lines showing different materials diffusing in others. For example, this is magnesium diffusing in magnesium oxide, nickel diffusing in magnesium oxide, and you find the values are very different, and you find that all of them are sloping such that you find that higher the temperature, higher is the diffusion. On the y axis here we have diffusivity, and we find that the values are higher when the temperature is higher. So, higher is the temperature, diffusion occurs faster, there is more diffusion. Coming back to the first aspect, we find that the diffusion depends on the crystal structure through which the diffusion is going to occur. For example, we find that in the BCC ion diffusion is faster than the FCC ion at the same temperature. For example, at 910 degrees there is an equal possibility that there is a BCC ion and an FCC ion, and the reason is that the BCC structure is less closely packed. This we saw a couple of lectures back, that the BCC structure was the least of the closely packed structures that we saw. So, when the structure is less closely packed, diffusion can occur more easily because the other atoms can move more freely in the lattice structure. There are also other cases where you can have fast diffusion paths, and this becomes very important when we look later at corrosion and so on, because we find that diffusion occurs more rapidly, diffusion paths are faster along grain boundaries and dislocation cores. And if you remember, these are the defects that occur in the lattice structure, grain boundary being a surface defect and dislocation being a line defect. The grain boundary acts as a 2 atom wide planar channel. So, you have the grain boundary here which is now like a path, a channel for diffusion to occur. So, diffusion occurs very fast to the grain boundary. Also in a dislocation core here you find that the diffusion will act fast. Dislocation core acts as a 2 atom wide high conductivity tube. So, through this, because of the higher energy, the diffusion can occur faster, and this is seen here in this diagram from Ashby and Jones, where you see diffusivity on the y axis, temperature on the x axis, and here you see how the behavior is. Diffusion is across at the surface, grain boundary, and in the bulk well within a crystal. You find the diffusivity is very high on a surface because you have discontinuity there, you have a surface that is exposed. Next will come the diffusion along a grain boundary, again because the surface defect will allow the atoms to diffuse along the grain boundary, whereas within the bulk of the material diffusion will be slower, less diffusion will occur. In all the cases diffusion will be higher at higher temperature. Here you see temperature increasing to the left in this diagram, and we find that as the temperature increases we find the diffusivity or the speed at which diffusion is occurring will be more. So, to conclude, we have looked at different ways that atoms can move within a lattice structure. We saw how small movements leads to elastic deformation, that is when the force is removed the atoms go back to their original structure. Then we have larger deformations occurring, plastic deformations occurring due to large strains within the lattice structure. Dislocation movement, we also looked at how diffusion occurs where atoms can move over large distances to the crystal structure, and we looked at different types of diffusion and saw how diffusion is affected by temperature. What we saw is that diffusion is faster through certain defects like dislocation cores and grain boundaries. We also saw that diffusion was higher when the temperature is higher, and one interesting aspect that came up was how grain boundaries are barriers to dislocation movement. So we found that because of the misorientation of the crystal planes across the grain boundary, the dislocation cannot move through one grain and on to another, and therefore we concluded that if we have lot of grain boundaries like in a material which has small grains, there would be higher barriers or more energy needed for shearing of that material, leading to higher yield strength. We also looked at how impurities, say in alloys, can increase the strength because they cause the slip planes to be non-planar. There is a distortion of the lattice, and therefore we found that the dislocation movement is hindered, and therefore you have higher strength in alloys than in a pure material. In the next lecture we look at how the microstructure develops, we look at how phase changes occur in different materials, and that will lead us on to understanding the behavior of the materials, the surface properties and the mechanical properties of different materials. Thank you. We will now look at a few questions that could arise regarding the lecture on the movement of atoms.
Sir, you had discussed that slip will easily occur in closely packed planes. Why is it that it is easy in closely packed planes, and what if it is loosely packed?
Yeah. See, what happens is it is not that the slip occurs in the plane, but along the planes. So when you have a very closely packed structure, slip is very difficult to occur across these planes. So the planes which are closely packed slip against each other. So the slipping is occurring along the planes because it is very difficult for slip to occur across these planes where more bonds have to be broken. Now if you have a closely packed plane, then the slip will occur along those planes rather than any other plane which is more loosely packed. Okay.
Can you explain what is the effect of grain size and grain boundaries on the ductility of the material?
See, when we looked at the movement of dislocations, we said that the dislocations are hindered by the grain boundaries. So when you have a lot of grain boundaries, there is more hindrance, so there is a restriction of slip, or you need a very high shear force to cause slip to occur. And this is the reason why we have strain hardening after a certain amount of slip or yielding, the hindrance by the grain boundaries to the dislocations, and this leads to strain hardening because more energy is required, more shear forces are required to continue with the slip that has occurred due to the yielding. So the ductility is affected by the amount of grain boundaries that you have. More grain boundaries, you would expect the metal to be less ductile, in the sense that the final elongation at failure will be less, but the strength will be higher because you have more hindrance to the dislocations, more barriers to the dislocations. So the stress that is required for slip to occur is higher. So the strength will go up, but the elongation would normally decrease if you have small grains leading to many grain boundaries in the system.